Good afternoon, Prof. My name is Matsapo Majeja. I will be taking you through my TPG3700 design project. It's an upgrade of a provincial road D889 in the Mopani district, Limpopo province. The length of the alignment is 3820 kilometers. The purpose of this project is to determine and define design parameters, required studies, and improvements. The scope of this project include the upgrade of a gravel road to a 4-lane divided road, major road. The task includes the concept design criteria, surveys, material investigations, and regulatory compliance as per TRH4, TRH26, and also the Sundial guidelines. The project description, it is located in Tzaneen local municipality, Mopani district, Limpopo province. It's linking R36 and rural peri-urban settlements. The motivation of this upgrade is that the traffic growth, regional connectivity, and safety and capacity needs to be improved because the traffic growth rate keeps on increasing. I will discuss this in my next slide. The site conditions includes the topography is a flat to gently undulating slopes. The geology, as per the picture on the right, it's of magmatite and granite intrusions, and the climate, it's warm temperatures, which with 414 millimeter annual rainfall. The Waynard value is less than 2. It's a wet region. In general, less rain is expected between the months of June to August, and the month with the most rain is usually February. As you can see on the diagram below that we do experience a lot of rain from October to March. The traffic analysis was conducted on the alignment because during design now, the AADTs are 3,000 vehicles per day, but this should increase over the next 15 years period, design period years. For the alignment. The data was collected from RAL. It was conducted in 2022, and the projected growth rate is 3% to 5% per year. The traffic loading over the 15 years is 0.5 to 1.0 MESA. The category of the road is a category C road according to TRH4. The pavement design that I have opted for, as I've explained previously, the Waynard value is less than 2. It means that we are working with a wet region, and as calculated at the opening of traffic after 3 years, we are going to experience a 3% growth rate factor, which I did calculated the ADTs, and also I've also calculated the remainder of the SDP for the over the 15 years, which means we will be looking at 15 and we will be looking at 5,000 ADTs, meaning that AADTs, meaning that the road will be experiencing high volumes, meaning that we need to choose a very better pavement design structure. So we have these categories. I looked at TRH4 tables, and under category C and ES10, the pavement class is being identified as ES10, meaning that we have no options there, but we have to opt for better structures, pavement structures, meaning we have option 1, option 2, and option 3. The first option is asphalt of we're going to have a asphalt of 50 millimeters, and we're going to have a BTB base layer of 150 millimeters, and a fixed sub-base layer for 200 millimeter fixed sub-base layer, which will be converted to a C4. And we have calculated also the CBRs. There has been we have collected samples on the alignment and did our calculations for the CBR to get the 80% reliability, which we got our subgrade class as SG2, meaning that we will have a 150 millimeter thick G7 lower selected layer and a rip and recompact of the lower selected layer. We have option number 2 and option number 3, which I have discussed in my report. Geometric design, we looked at the design speed. The design speed is 80 kilometers per hour. Actually, we are targeting 80 kilometers per hour to 100 to make it a class 2 road. Currently, it's sitting at 80 kilometers per hour. The horizontal radius across the alignment is 230 meters, which I have checked this if it is adequate for our curve. And I have included this in my report. It is adequate, and the 230-meter is adaptable. The vertical curves, I have manual calculations for the SIR curve, and we checked for the K value requirements, and also checking the adequacy of the radius, and also checking if the free steering wheel a command is being met, of which all of these have been applicable and acceptable. The cross section of the road, it's a four-lane major road, meaning that we are going to have 4 lanes, and these lanes will be 3.5-meter wide and 0.8-meter shoulders on each side. As per TRH 26, the minimum shoulders is 0.8-meter. Shoulders, the earthworks and materials on our civil 3D designer. I have computed materials, meaning that we are going to have a cut and fill, where we will take the design level and also we minus it from the ground level. At some areas, it will be that the ground level is above the design level, meaning we are going to cut so we have a total cut of 62,282.44 cubic meters and a fill of 18,168.21 cubic meters. And the materials that will be used for our road, as discussed, if we are opting for option 1, this will depend on client needs and budget, meaning that we will have a G5 from the borrow pit and also a G7 from the borrow pit, and other materials will be commercially sourced. The drainage design, I've carried out the drainage design for this project, and we found that because it's a wet region, they experience a lot of rain. We found that there's an existing earth drain along the alignment, and there's a need for upgrading this earth drain to a V drain, and also introducing subsoil drainage, and also there has been culverts along the road that the community themselves, they have gathered money and constructed these, but these need to be upgraded or replaced. These were calculated on the catchment area. The rational method for catchments and culverts upgrade and extensions are recommended. We are going to look on central drainage manuals to check if how much catchment are we looking at, and also to check the sizing of the pipes of the culverts. Conclusions and recommendations. I am going to recommend this upgrade because it has met geometrical standards, because we're looking at an 80 kilometer per hour design speed. And if we're looking at the free steering wheel, drivers will be able to turn on our radius of 230, and also that this upgrade will serve the mall near the alignment, because in the future, in 15 years, after 12 years after we've opened the road, the traffic will grow, and there will be a need to upgrade this road into a class 2 arterial road, because now the traffic there is a bit congested, because now there is schools around the area, and as I was saying, there are schools around the area in the mall. So there's a need to upgrade this road into a class 2 road. There are pavement walkways, and this should tell you that we can upgrade it because there's a need to accommodate more traffic. The drainage and pavement needs upgrades. This is a very wet area because they do experience like 414 millimeter rain. It means that there's a need to upgrade the drainage structures that are currently in place, and also look into vegetation control, because when it rains, it tends to grow weeds and all of that. So we need to also look into landscaping, and also the recommended pavement layers and material sources. Looking at the 3,000, I mean the projected traffic growth rate of 5.5%, we do need a better structure that can withstand these live loads, and also to sustain and better better perform during its serviceability limit and design period, so that we are looking at a structure that won't collapse in the next 3 years, because of as and when the traffic grows, it will affect the life of the pavement. So judging by our options, a BTB is a very stronger base compared to the others, and also the other materials that have been chosen. The thickness of the asphalt of 50 millimeters will come in as an advantage for the heavy traffics on the alignment. Thank you, Prof. I've also checked against TRH 24, I mean TRH 26 and TRH 4 and TRH 17 to check my design if it is acceptable, and I can confidently say that we have achieved and met all of these. Thank you.